describe the grading statistic. Okay, so and then how to detect the topological defects? We can calculate the topological entanglement entropy. Then, if we put our wave function on a disk and with a smooth cut with a length of L, then we know the topological entanglement entropy have the form is the area term and minus the constant gamma. Then the gamma is universal in the topological. So the gamma is the topological entanglement entropy. And then we know the gamma is related to the quantum number D. So for example, for the D2 liquid, the gamma is equal to log 2. And numerically, how to obtain the topological entanglement entropy? So we can calculate the entanglement entropy for different size, and by subtract the area term, and then we can get the topological entanglement entropy gamma. Then, however, we know the topological entanglement entropy gamma will depend on the ground state. If the cut is non-trivial bipartition. And then the special basis of the ground state with a minimally entangled state. So it's called the minimally with a minimally entanglement. So they call it the minimally entangled state. So in particular, then the minimally entangled state can be used to describe the quasi-particle wave function. Okay, this is an important thing for our calculation. Okay, so now I was giving you my motivation. So we know the topological order for the topological order phase. If we consider the global symmetry, then the symmetry will enrich the topological order phase. So they call the symmetry enriched topological order phase. And then by using the local unitary transformation, if we consider the symmetry, so we can find there are more kind of case. So for example, if we consider a torical model, we know this one is the D2 topological order phase. However, if we consider another phase is the RVB phase on the kagome lattice, this phase is a D2 topological order phase. And for the each bond is a singlet, so it has a SO3, SU2 symmetry. So, and then we know once we break the symmetry, once we break one singlet, a pair of the quasi-particle are created. So here we would like to ask a question, how to detect the SET phase. And another question is how the symmetry enrich the topological order. Okay, so here we would like to introduce you the philosophy is symmetry fractionalization. For example, we consider the Laughlin states, the fractional quantum Hall effect. If we adhere one electron in the fractional quantum Hall effect, so that means if this system has a U1 symmetry, so we know the quasi-particle will carry the fractional charge E/3. And then another case is the RVB phase on the kagome lattice. This phase is a D2 topological order phase. And once we break the one singlet, so a pair of defect will carry a spin 1/2 particle. So from those two cases, we know if the topological order phase has a symmetry, then the quasi-particle will carry the fractional symmetry representation. Okay, so now if we consider a topological order phase, then it did not break any symmetry. So the Hamiltonian and the ground state has the same symmetry. So once a pair of quasi-particle are created, then under the global symmetry, then the quasi-particle will carry the projective representation. Once we can measure the projective representation carried by the quasi-particle, and then we can classify it. So we can put our wave function on the torus, then then we know the minimally entangled state will given us a quasi-particle wave function, and the quasi-particle will appear at the end of the cut, and then under the global symmetry, the quasi-particle will carry the projective representation. And numerically, it can be understood by the second cohomology group. Okay, so here let me summarize some property of D2 topological order phase. We know for the D2 topological order phase, it has 4 degeneracy on the torus, and it has 4 type of quasi-particle type. And the minimally entangled state will give us a quasi-particle wave function. And then the good thing is the tensor product state is a good tool to represent the quasi-particle wave function. We just inserting some string operator and or choose a different boundary, we can get a different quasi-particle wave function. Okay, so in the following, we will consider a spin 1/2 representation on the D2 gate charge. And then I will show you how to detect the symmetry enriched topological order phase. So here, I consider example is equal weight superposition of all closed loop of spin 1 AKOT chain on the honeycomb lattice like this. If we did not consider the internal symmetry, we know this phase is D2 topological on the honeycomb lattice. However, if we break the one, because for each closed loop is S1 S equal to 1 AKOT chain. Once we break the one closed loop, then the quasi-particle will carry the spin 1/2 and appear at the end of the chain. So this is the case of the spin 1/2 representation carried by the D2 gauge charge. And then this phase can be represented by the tensor product state. And we can build up this phase by using a spin 1 boson on the honeycomb lattice. Okay, and then the tensor product state like this, we can prepare some maximal entangled state and do some projection. And then we write down our wave function by using the tensor product state and then put it in the long cylinder. So we can calculate the topological entanglement entropy. So once we increase the circumference of the cylinder, then we can find the topological entanglement entropy will be close to log 2. So we know this phase is a D2 topological order phase. And then by inserting the symmetry operator to our wave function to form a generalized transfer matrix. So we can map our 2-dimensional tensor product state to a 1-dimensional effective metric product state. And then we can obtain the projective representation. So from the we consider the time reversal and the D2 cross D2 symmetry. Then from the commutator, we find for the quasi-particle E and the bound state F, we have a non-trivial phase factor -1. So this is evidence for the special SET phase. On the other hand, we can calculate, we can define the non-local order parameter. It is overlap between the quasi-particle wave function with a string operator G. So we can choose the symmetry we want, such as we can choose the rotation operator. And then from our calculation result, we find for the quasi-particle E and F, the non-local order parameter will vanish. So if the H state is fractionalized. So again, we prove this phase is a special SET phase. And then another case is RBB phase on the kagome lattice. Then we know this phase is a D2 topological order phase, and it is a good approximate of the hexagonal model on the kagome lattice. So again, once we break one singlet, a pair of defect will carry the spin 1/2. So again, this phase is a spin 1/2 representation carried by the D2 gate charge. And then also we can put our wave function on a long cylinder to obtain the topological entanglement entropy. It's close to the log 2. So this phase is a D2 topological phase. And then we also can inserting the symmetry operator, and then we can get the projective representation. And so again, we can find from the projective representation and the non-local order parameter, we can find this phase is special SET phase. And then we also can set the AKLT AKLT string state and the SET and the RVB phase is below the same class. Okay, so let me conclude this work. So we know the symmetry will enrich the topological order phase called the symmetry enriched topological order phase. And then we propose a method to detect the symmetry SET phase by measure the projective representation and the non-local order parameter. And here we just consider the abelian case. So in the following, or in the future, I would like to generalize this idea to the non-abelian case. And in our work, we just start from some wave function. So in the future, we would like to start from some Hamiltonian, and we can solve this Hamiltonian and obtain the wave function and try to classify it. And just think maybe this SET phase also can be used to quantum computation, because for the one-dimensional AKLT and the two-dimensional AKLT is a good tool for the quantum computer. So maybe the SET phase also is a good resource for the quantum computer. So thank you for your attention.
Question or comment?
So this fixed point tensor you get from the state RG.
Yes.
Can you use that as a tool to distinguish different states, or you always have to calculate some expectation value?
Yeah, we just calculate some. I calculate the S1 divided by S2, just a local tensor by different contraction.
But looking at the tensor elements, we cannot really get any.
Because we have some gauge transformation. Yeah. So I think that if you just see the tensor elements, hard to determine what kind of phase. So.
I just want to ask quickly. So, what is the relation between the? So, is there a simple relation between the ground state and the genus of the space you consider, or it's just very like a theoretic, like a model?
You mean a G?
Yeah, G and G.
Yes, you.
So I'm not familiar with this.
The G is related to your geometry, but we also relate the number of the ground state is the n of G. So the n is depend on your model.
Yeah.
Yeah. Yeah. Yeah.
Yes. You mentioned that this AKLT system has a potential application to quantum computing.
Mm-hmm.
And in some realizations, it requires torus with many genuses. The number of genuses is proportional. The number of qubits is proportional to the number of genuses. Do you have the same problem in your realization, potential realization?
You mean for the quantum computer?
Yes.
I think I just think maybe we can use SET as a resource. I just think.
But you need to define qubits.
Yes, right.
Qubit.
Yeah. So Actually, I don't know. I just have this idea, but I don't know how to define the qubits now. Yeah.
Each speed. I think you were mentioning the surface current.
Yeah.
That's a topological.
But in that order, each thing can be a cube.
But it's not topological. It can be mixed up with people with three dimensions.
I have a question. So at the end of the talk, you mentioned about the generalization of to non-abelian cases, right?
Yes.
So, is there a hint? I mean, so is the method that you give here be good enough to discuss about the non-abelian case, or is there, or do we need anything more?
You mean for our method?
Yeah.
Because I'm not sure for the non-binary case, it also have some property. Is the quasi-particle. We also can detect the SET by using we know the quasi-particle carry a projective representation. For the abelian case, is correct, but for the non-abelian case, I'm not sure. So.
If there is no further questions, let's take the speaker. And this concludes the morning session.